Good afternoon. Yes, you know very well, we have to continue, unfortunately, this way. So unfortunately, with remotely the lectures themselves. So yeah, here we go. The project, as I wrote you in the email yesterday, the project today will take place normally. So from 1 to 3 at the university. So if any of you has any questions, you can always write me an email, or if you need a private session over Zoom, then you can write me an email. Otherwise, the consultations are tomorrow in my room, in room 244, to 132, but 244. So you are welcome to come if you have any questions. For those that finished the PCBs and uploaded them on the portal, they are in the work. So currently I'm busy taking care about the formal stuff, so to order the board, but I have a green light. I got the green light to do this, to make them physically. So I'm proceeding with the manufacturing and with all the necessary formalities. Hopefully end of next week. There is a chance, maybe the beginning of the next week, to have the boards physically. Then I will deliver them to you. So they will be available. Okay. Any questions? Maybe before we begin. No questions. Okay. Hopefully you can see me and hear me well. Okay, we finished before Christmas and New Year break. We finished summer here with the analysis of the communication interfaces. We talked about parallel interfaces that are most common in microcontrollers, or commonly used in microcontrollers. The basic one at least. So today, quite often we're using also various variations of those interfaces, like, for example, DCMI. Yet we'll try to talk more about them next semester. Yet a very important role in every embedded systems play serial interfaces. You have some experience, at least in connecting the interfaces, because of the project. So the first one we talked about was the UART interface, and the second one, the SPI. SPI, the interface, which is beautiful, very beautiful for me, because it's simple. The simplicity of this interface you can see on the slide. So the hardware simplicity of this interface, where we have just two registers, input and output. So two registers with parallel input, serial input, parallel output, and serial output, because these registers are accessible from all four directions. The master of this data transfer drives the S clock line, while the data transferred from master to slave are delivered through the MOSI line, and the data back are delivered through the MESO line. And the data transfer is always taking place in two directions at the same time. So actually, it's neither a half duplex nor a full duplex. I call it, this is 3/4 duplex, because it's somewhere in between. Because take a look, we've got for full duplex data transfer, we've got the transfer going on at the same time, while with half duplex we have one common line and the data transfer is going either in one direction or in the other. Here we've got the data transfer going on in the same direction, in both directions at the same time. That's true. They are two dedicated lines. That's true. Like, that's the same like for any duplex operation, full duplex. But the slave is not able to send anything to master if the master doesn't drive the SCLK line. Thus, does those three-quarter duplex. The data transfer in case of SPI is by default 8-bit. It's similar to UART, because in UART, as you shall remember, we have one start bit, 8 bits of data, and one stop bit, because the data transfer is 8-bit wise or byte wise. Here, so the bytes here can be in UART can be 7 bits as well, so it's 7 or 8 bits. Here in SPI by default is the 8-bit data transfer, although various microcontrollers allow to change, to modify this. So sometimes this became quite common features. We've got even 16, 8 or 16, so there is a choice if the data transfer is 8-bit wise or 16-bit wise, but rather not more. If we want to transfer more bits than 16, what we need to do is we need to use a DMA mechanism or some FIFO, so first in, first out, in order to automatize the data transfer between the master and the slave. In case of configuration or configurability of the SPI, it's not the greatest, I would say. So the configurability here is only, so we don't configure we have to configure the clock speed or the baud rate, like is the case for UART, but the baud rate here is configured in a simple way, because the reception is synchronous to the transmission, which means that the clock rate can vary even during data transfer. So which means that we can stop the data transfer for infinite time and renew it, and no data bit should vanish. No, we should not lose any data bit during this data transfer. That's fantastic about the SPI. So the SPI actually may be clocked from 0 to some value. Usually we are limited to something like 20 megahertz, although as I mentioned already, on the market you can find chips or microcontrollers capable of clock value exceeding 20, so closer to 40 megahertz, 40, 50 even. So the baud rate is configuration of the baud rate this time is very simple. What we need to configure is the phase and the polarity of the clock. So CPOL and CPHA, so two configuration bits. In case of CPOL, means the polarization of the clock in the inactive state. So CPOL 0 means that in the inactive state the clock is logic low. In CPOL 1, that it's logic high. CPHA then tells us if the data are active on the rising or falling edge, so that's CPHA 0, that's active on rising edge, and CPH1 data are active on falling edge. So that's the blue line. So CPHA 0 is here, CPH1 is here. Slave select, as we mentioned last time, is for selecting the slave that we talked to. So it depends on the configuration. Again, we have usually a configuration of a bus where everybody sees the data. Configuration of S clock, MISO and MOSI is as of a bus, which means that we need, in order to access the particular nodes, we need to inform the nodes or enable the nodes through a dedicated signal, and this signal, the slave select, is playing this role. In case of microcontrollers, usually we have in microcontroller 4 pins, so MISO, MOSI and slave select. Sometimes those pins are marked as the in, and this pin is marked sometimes as the out, because this is data out, must output is data out, must input is data in. But mark that usually we have just one slave select, which means that automatically, or with the use of the SPI peripheral, a microcontroller can drive only one slave. If you want to connect more slaves, you need to prepare a second line, or use a second general purpose line that you have available in microcontroller, second, third, fourth, fifth, whatever, how many devices you want to connect to one SPI, unit. Now here is the configuration as mentioned. So clock lines are connected, MOSI lines are connected, MISO lines are connected, slave selects have to be chosen. So one slave select is usually available within one SPI peripheral, while the other slave selects have to be adapted from and driven manually, because that's the worst here, from the other lines, general purpose lines. One remark again. I don't like the remote lectures because I can't see you and I can't hear you, and I don't have any feedback from you. So if I'm not clear in anything, raise your hand or try to use a chat or try to intercept me with your voice. Then I have some information that you don't get something or that I'm not clear enough explaining something. So don't forget to stop me if something is not clear. There is a configuration of daisy chain available. The daisy chain configuration is a configuration where there is a chain, so that's why chain the name. So here is a chain. So this configuration does not require multiple slave select lines. So just one slave select line is there. So this configuration from hardware point of view is easier and simpler, yet then we need to add addressing over the in case of frames on the frame level, and SPI itself is not defining any frames, so it's on the in the layered model is the physical layer only. We don't even have medium access control. So the medium access control layer here is non-existing, in fact, which means that we need to, if we want to use a daisy chain, we need to, from practical point of view, deliver, so add to our SPI communication software layer. That's not difficult, to be honest. That's not very difficult, but it's not difficult if the slaves are programmable. So if there are different microcontrollers, for example, then yeah, this daisy chain can be used. But if you want to connect in a daisy chain, the usual elements that we connect, like memories, like converters, like sensors, then no, they are not programmable and they are not supporting daisy chain. That's why the daisy chain is not really a good solution. The SPI, usually the only useful solution in SPI is the data path configuration. That's also a serious disadvantage. So this feature is also a serious disadvantage because, to be honest, there are two weak points of the SPI. So the beauty of simplicity of hardware configuration and of hardware data transfer. So this is the bright side. The dark side here is the necessity to connect so many pins. And so many pins because we've got clock, MISO, MOSI, and slave select. So at least 4 pins are necessary. Comparing to just 2 pins in UART, so 2 pins more. That's problem number 1. And the problem number 2, so the darkest of the darkest, is the necessity to have multiple slave select lines. Multiple slave select lines, and especially the necessity because, okay, if we have a microcontroller with 60, 80 pins, so 2, 3 more pins is not a problem. The problem is, unfortunately, that those additional slave select lines we have to usually drive manually, and this takes time. This simply takes time. So it doesn't seem problematic, but believe me, it is when you are doing something time critical, when you are dealing with some serious applications, then spending some additional time just manipulating with slave select bit, yuck. That's why we have the I2C interface for multiple slave connections. But about the I2C in a short moment. In case of the of an example, how the SPI is constructed, how simple it is, I'm showing you right now the diagram, the block diagram of the SPI block in 32-bit microcontroller, so in STM32 to F4 in this family. Mind how simple it is now. So the baud rate, we've got just 3 bits for generation. Remember the UART with the fractional generator and with all these nuances about clock generation. Here we've got just a baud rate with just 3 bits to generate the baud rate, and usually it is so. So usually in microcontrollers, however complicated the microcontroller is, baud rate is usually simple, because right now here it's not really a problem. Then we've got the configuration if a device is a master or slave, because microcontroller has a choice here. If you are connecting an ADC converter or a memory, then it's a slave. But if there is a microcontroller, it may be master or a slave. Yet to be able to be a master or a slave, there must be a special switching circuit, which is here, which is used to physically switch MOSI and MISO lines. Because that's the third serious disadvantage of the SPI interface, is that the functionality of the device is usually dependent on the hardware connections. It cannot be usually changed in software unless we have this kind of chip. Yeah, the QSPI, because there is a question about the QSPI. The QSPI, yeah, let's put aside for a moment, because the QSPI is an extension of the SPI itself, but it's not such a completely trivial extension. So about the QSPI, we'll talk more about a bit later. So let's put QSPI aside for this moment, not to blur the picture, because in fact QSPI is a different interface. So it's a special interface, more configurable for higher performance. But yeah, let's put it aside because I would like to mention about the QSPI a bit later when we talk about a bit more complex interfaces, because it's SPI, but it's a combination of SPI and parallel interface. But let's not blur the picture. So I would evade the answer to this question for this particular moment, as this is a different interface. So be patient. We'll talk about QSPI when the time comes, because it's a bit different interface. Going back, we've got this shift register here. So simple thing, and just 2 configuration registers with simple configuration. Of course, we've got a couple of things to configure here, but not too many, to be honest. We've got the DMA as well. We've got the DMA with the use of flags, and this is happening automatically, usually in microcontrollers as well. So like in case of the UART, also there should be DMA. Yeah, here is the DMA where the data is being transferred automatically out of the SPI and towards the SPI by the DMA block, depending on the previous configuration of the DMA block. And as with the case of UART before, also in case of SPI, I really deeply recommend the use of DMA in the operation. So unless we have no DMA, because the DMA is not present in small 8-bit microcontrollers, then sometimes we've got a simplified DMA, as I call it sometimes, so the FIFO or FIFO. Yet if there is a DMA, so if we have a chance to transmit and or receive more bytes automatically or semi-automatically, so it's very useful to configure and use it. Here it is less critical than in case of UART, because the SPI is much faster and much more energy efficient interface. Still, DMA is definitely worth using. The simplicity of the SPI to finish this interface, the analysis of this interface, can be clearly seen here with the interrupts and how few various flags are there to be monitored, and how few flags are generated, how few events are generating the interrupts in this processor. So these are the just the transmit receive flag, so simple thing, and 4 flags generating error interrupts. So just mark that just 3 interrupts, even in this pretty large and fast and efficient processor. So that's the beauty of this SPI, that it's simple. We can't say this about the I2C interface, although the idea about the I2C interface is to be able to connect multiple devices to the data bus without the need to expand the to increase the number of physical lines. Because in case of I2C, we can connect tens of devices, so physically, theoretically more than 100, but in practice we talk about numbers going in 10, maybe a bit more than 10, but I have never seen a network of more than 10 I2C units, but theoretically it's possible to just 2 lines. So it's always 2 lines. So we have always just 2 lines in I2C, so clock line and data line. To those lines we connect multiple devices. Yet, if we think about it a bit, then we can see that, okay, if we want to connect multiple devices, there must be some method of addressing the communication between the devices. And that's the reason why in I2C interfaces, unlike in the 2 previously mentioned, not only we have the physical layer defined, but also we have medium access control layer defined with frame and with addressing. And that's the difference, the major difference between I2C and SPI. So these are the main differences. The other differences are, so two wire serial interface. It's used for serial internal communication. So the range of use of I2C is same like SPI, and actually those 2 interfaces are competing with each other, if we can say it this way. So sometimes we have to decide. We are buying a device supporting I2C, or there is a version supporting SPI. Sometimes the devices are supporting both interfaces, and you switch it in software or in hardware, which interface is used for communication. So is it SPI, SPI, or is it I2C? Still, these are interfaces used for the same. UART, remember, is used mainly for communication between our device and a PC or some module outside of the physical in different room, in different physical place. We've got also master-slave architecture, so it's another feature of the I2C. Yet here, then we have so-called multi-master configuration. So by default, by design, maybe not by default, but by design, the I2C works in a multi-master, which means that any of those devices can be a master, because any of those devices can control a clock. Or talking from the other side, if a device controls a clock line, then it becomes automatically, it is named automatically a master of data transfer. That's the way it is. So it's completely different from SPI, where in SPI we've got the single master architecture, single master slave architecture, and the master slave configuration is fixed in hardware. Here in I2C, it is here in I2C, it is a software tape. It is defined by software. We also use a TTL logic. It's for internal communication. So TTL logic or CMOS logic is used with voltages used. They have to be agreed upon, because you can use I2C for communication between 1.8 volt logic devices or between 5 volt logic devices. There is a problem if you want to communicate, if you want to use 1.8 volt here, for example, and 5 volt here device, yet it is not impossible to communicate them, to be honest. So maybe 1.8 volt is a bit questionable, so sometimes need some additional buffers. But for example, communicating if a device is 2.0 volt supporting only 2.5 volt logic and another one is supporting 5 volt logic on the line, in case of I2C interface, it is possible to communicate those devices together. That's also a bit special comparing to other interfaces. Fully synchronous data transfer controlled by the master, but this time we've got half duplex data transfer, so no guessing if this is full duplex or 3/4 duplex. It's half duplex because the transfer is going either from the master to the slave or from the slave to the master. The transmission is point to point, but we've got a network, we've got a bus here. Clearly we've got a bus with all devices connected to the bus. The bus consists of two lines of clock and data, as mentioned. The problem in I2C, and one of a few disadvantages of this interface, is slow data rate. So unfortunately, the data rate compared to SPI is very slow. So SPI, we talk about tens of megabits per second, and the limitations are mainly because of the physical limitations of the single-ended line that we are using. So if we change the SPI to MISO-MOSI line and clock line to differential lines, then with SPI, I can see no problems with transmitting speeds exceeding 100 megabits per second. In case of I2C interface, it's not so. So in order to, because of the compatibility problems and electrical troubles, the data rate is very limited. So here, as you can see, 400 kilobits per second is the major data rate, up to 400 kilobits per second. Theoretically, there is a special high-speed mode allowing 3.4 megabits per second, but it has to be supported by the module, and this is not common. The common speed, so usually we have just the data rate of 400 kilobits per second, nothing more. So that's one of the serious disadvantages. How the communication is going? So we have two lines. We have the half duplex, and we have multiple devices on the line, which means that kind of line arbitration has to go on. This is called line arbitration. There was no such a problem in UART because this was just point to point. There was no such a problem in case of SPI, because the master, there is just one master, and the master controls the data transfer by driving the appropriate slave select line. But there is a problem of this here, because we have a medium, so the lines SDA and SCL, which are common, which are multiple accessed by all the nodes that are connected to the line. The mechanism that we are using here is called carrier sense multiple access with collision detection, we can call it, because we are what the devices are doing. So each node is checking out the line. Yeah, it's called carrier sensing, although as a carrier here, we've got the data transfer going on. So the devices are checking if the line is switching, if there are any low states on the line, because normally in the idle state, the SDA and SCL line here are always high. In SPI, we could configure it. In case of I2C, it's non-configurable. So the SDA and SCL line in the inactive state, they are always high, and they are not changing, they are not altering. So that's what I call my CS, so carrier sensing. This is the carrier sensing. So if there is a DC carrier, then absent, so if there is any switching present, in other words, then it means that there is a transmission going on, and then it means that the node that wants to transmit should wait and should monitor the line and wait for the end of data transfer, because each transfer then has two special conditions of the start bit and stop bit. It's also a special thing not found in I2C, in SPI comparing, although available in UART. So the start and stop bit. Here the start bit, by start bit we understand the state where at the high of the SCL line, SDA falls down, and the stop bit is the reverse one. So during the high state of the SCL, the SDA is rising from low state to high state. During the bit data transfer, any transition of N on SDA line is allowed only during low state of the clock. It's very characteristic to I2C. So if there is a transition of SDA line on SCL line, it means starts or stop bit of the data transfer. If there is a transition on the low state of SCL line, it means a data bit. A data bit being transferred. So this is very special. What other things are special? The lines are open drain tape here, so we don't have a push pulls. But in case to keep the parameters proper, in order to keep the interoperability here between the devices, we have to make the lines open drain. Both lines are pulled out as well, because if we have an open drain, at some point, somewhere we need a pull up. We talked about it a couple of lectures ago, I was trying to show you that the pull-ups are sometimes available, but even if they are not available in the microcontroller, then we have to add the pull-up externally as external registers. Resistors, of course, not registers. Resistors. Okay, but that's not all. That is still the physical layer, and I mentioned that in case of I2C, we've got also medium access control layer, so the layer with the addressing. How's it working? The data transfer in I2C always begins with. So the data transfer, first of all, is always byte-wide, because we've got. As you can see here on the slide, there is always transmission when the master, whoever is the master, starts the data transfer. It transfers first the 8 bits of data, and then during 9 bits of data, we've got so-called acknowledgement bit. So it's still a hardware. So sorry about preemptive mark, because we still have one thing about the hardware about the physical layer that needs to be clarified, and which is also very unique to I2C, which means that we've got each 1 byte of data transfer is here acknowledged in hardware. Again, it's something not found in I2C, in SPI and in UART, where acknowledgement has to be done in software. Acknowledgement has to be done by software. Here, the acknowledgement is totally and fully done by the hardware, but through this acknowledgement bit. So the master, take a look how it works. The master first clocks in the first 8 bits, driving the SDA line. Then during 9th clock cycle, driven by the master starts to listen to the line, and if a slave understood the message, then it pulls the line low. If a slave did not understood the message, then the line keeps high or stays high. The SDA line. It means that for the master, it means that the byte was not acknowledged. Take a look. Each byte here of the data transfer is acknowledged. And that's also the reason why in I2C, the data transfer is like in UART, 8-bit wide, always. So we are not, unlike maybe, because in UART, we have a 7-bit data transfer, we've got 8-bit data transfer, we've got 9-bit data transfer. Here, in case of I2C, everything is completely fixed around 8 bits. So we have 8-bit data transfer, then goes the acknowledge. So the one chunk of information consists of 9 clocking cycles, So that's the acknowledge. That's the physical line. That's the physical part. So now, what about the MAC part? You can see already it on the slide. So when the data transfer starts, in case of I2C, the first byte transferred is always the address of the slave. It's that simple. So there is a frame, but the frame is that simple, that trivial. So we've got first of all the information about to whom the frame is addressed, so the following data are addressed. So there is a slave address, 7-bit mind that slave address, and then we have the 8-bit, which tells us if we want to write to the slave. So if the 8-bit of the address byte is logic low, then it means that the next consecutive byte will be written from the master to the slave, and if it is high, then it means that the next data are to be read. So it means that the master wants to read something from the slave. Only then, after this only after this address byte transferred, we've got the nomad transmission going on, and the nomad transmission. Yeah, an example of the transmission we've got here. So in this line, so we've got the start bit, then we've got the address byte, the direct with the acknowledgement. In the address byte here, we've got the read write. But if a master wants to transmit, then it means that we've got, as the 8-bit, we've got a 0, and then we've got the acknowledgement coming from the slave, and then the master starts to transfer bytes. First byte of data, acknowledge, second byte of data, acknowledge, and any byte of data, any number of data which it wants, which it would like, unless any of the data is not acknowledged. Because if a slave wants to stop the data transfer because it's not interested, or because it has something more interested to do, then it's enough that it's not acknowledging any of the data, and then the master automatically stops the data transfer, generating the stop condition. So that's how the transmission is going on. But mind that, so it's not that trivial, but it's not, unfortunately, the only way the communication is going on, because that's the example from the point of view of the master. If our microcontroller is a master and it wants to transmit something, but of course we've got 4 combinations, so we may have a situation that the master wants to read some data. Then we have a combination. Then there is a start bit, master sends the address, but on the 9th bit sets 1, means that it wants to read the data. The acknowledgement then first comes from the slave. So this is the acknowledgement that comes from the slave. But then master still clocks the data, controls the clock line, so generates the clock data. But this here, starting from this point, master starts to read the SDA line. So it's not driving it anymore. This time master confirms the data by setting the acknowledge. So now the data fields are controlled by the slave, while the acknowledgement is controlled by the master. So this time, take a look. It's different than it used to be. So we change the functionality by that. So the slave controls this acknowledgement only, while master controls this acknowledgement field, this, and this acknowledgement field. Here is non-acknowledged, but it may be acknowledgement as well. And the master controls naturally the stop, because master always controls the start and stop. Start and stop, not, and it's not dependent on the direction or functionality of the master. But of course, if our microcontroller may be a master, then it may be a slave as well. So we have also 2 options where our microcontroller becomes a functionality of the slave. First, receiving, because this is the situations where some devices wants to transmit some data to us, and our microcontroller is to receive the data. Then during the reception part, naturally we are just accepting the address, because our slave has a certain address, so we have to accept the address, and accepting the address is done by toggling the data line during the acknowledgement phase, so during the 9th bit of operation. Then if we are to receive, then we are as a slave, this time reading the data. So when the data, we wait for the 8 clock cycles, we are reading the data, and then we are setting the acknowledge. Then we are reading the next data, we are setting the acknowledge, and so on. That's the functionality of the receiver. And the last option in I2C, the functionality of the transmitter. The functionality of the transmitter, where the start bit, of course, is generated by the master of the data transfer. Then we, as a slave, wait for the appropriate address, for our address, to be transmitted by the master. When the address is proper, then what we do is we as a slave, generate the acknowledgement, and then we start to transfer the data. So then the clock, with each clock cycle coming in from the master, we drive, as a slave this time, we drive the data line and wait for the acknowledge. So this time we are reading the acknowledgement line that is on the line, that is driven this time by the master of the transfer. As you can see, it's not simple anymore. It's not as trivial as in UART or in SPI. So it requires many more things to be going on. Although the good thing about it, remember, and this is the bright side always, is that we can have connected multiple devices on the line, multiple devices that, and each of those devices can transfer to any other devices on the bus independently. So of course not in the same time, but independently on each other. So this complexity about the 4 types of operations of master transmit, master receive, slave transmit, and slave receive, they are all coped by an I2C block in a microcontroller. Honestly speaking, the SPI, so if a microcontroller is missing for any reason, SPI, it's very unlikely, because SPI is so simple that even the smallest microcontrollers on the market, they have the SPI implemented. But if an SPI is missing, then I can imagine making the SPI by ourselves, thus making I2C manually by bit switching is definitely very, very bad idea, because there is so many things that need to be done. Then in order to cope with all those operations happening, so all those 4 different states of operation, and then doing it by ourselves is pretty nasty. That's why we are usually, if you want to use an I2C, always find a microcontroller with I2C controller inside integrated. So then it's only about configuration of this block. Yet configurations of this block is not always that trivial, because we have to configure this time a couple of things. Like for example, we have to decide and configure if our device is to be a master or a slave. If it is a master, we have to decide about the clock generation. Then we have to decide, should we generate start or stop, or when, how should we generate it, or when should we generate it? Because the next thing about the configurations of the master is how many bytes are to be transmitted or received. These are 2 things that we need to decide when configuring the master, because the data, the whole transfer any of this transfer, so for those categories, is controlled automatically by the controller. So of course there are many things happening, but in order to have everything running smoothly, we have to configure, and we are configuring the controller itself that does the job for us. But we need to configure, so that's nice, but we need to configure it properly before we start the data transfer. And that's not that simple, because of so many things, the number of things we need to configure. The second thing is that during the slave configurations, we have to, first of all, program the address that our slave is to react onto. Sometimes we have just one address, sometimes we can configure a range of addresses, sometimes we can configure a few addresses that our slave is to respond to, is to accept. And as well, I forget about it, in both those cases we have to point a memory where the data are, or where the data are to be placed. So plenty of things that need to be configured, and this also can be seen in the last slide that I wanted to show you. So in the number of interrupts that are serviced, so plenty of things can happen. Plenty of things can happen. If you're more interested into this, yeah, you can always read any documentation about the I2C block in any microcontroller. There is always a good description of those errors, possible problems, or just states, because these states are, yeah, you can see them here. So these are EV, these are events, and they are all depicted in status register, and we can always control at which state we are and where's how the frame is currently transmitted and how much is still left to be transmitted. Still plenty of information that needs to be serviced and analyzed. For this reason, for the beginners, I always discourage beginners of using I2C. So if you have a chance, always use SPI. SPI has certain disadvantages. We talked about them a few minutes ago. Yet it's simple to be used and simple to be analyzed and simple to be configured. In I2C, when it works very nicely, very smoothly. We can connect plenty of nodes to one bus. So you have just two lines that needs the two hardware lines that are connected between the nodes. Yet configuration and the usage and the throughput, not really. Okay, let's have a break. So 15-minute break normally. So to breathe out from this, and after the break, we'll get back. There's a question. Are there any address translate chips where could a program custom address or 128 address space is not big of an issue? Yes, you touched the very important problem of the I2C. So the addressing itself and the address space, which is just 7-bit wide. So if you want to have more addresses than 7-bit, you have to turn towards the 10-bit addressing, which is sometimes supported, and it's shown here. Then we have the address composed of so the header itself then is composed of 3 bytes, not just 1. In this mode, in this 10-bit master mode. The problem with 10-bit master, as you can imagine, instead of 128 nodes that we can connect, we have 1024 nodes. But the problem with this 10-bit, which is much more, but the problem with 10-bit addressing is that it's not really supported. So it's in microcontrollers, but not really available in the nodes. So usually we are stuck with the 7-bit addressing, and here indeed is a problem. Here indeed it's a problem, and the address collision is a problem. About the translation chip, so about the translation between different addresses, I haven't heard about any. So you can make a chip translation only with the use of microcontroller and 2 I2C interfaces, with 2 I2C interfaces, which is pretty nasty because you waste the microcontroller with 2 I2C interfaces to translate between the addresses. If you have a microcontroller with 2 I2C interfaces, why not to use it by connecting 2 different address spaces? Because then, yeah, you know, maybe I write it down. If you have a microcontroller with 2 I2C interfaces, then why to connect node 1 here to connect to the address space of the other nodes on the other side, if you can have 1 node address here and 1 node address here? So generally, I haven't heard about about this node, about the address translation, realized that has any physical sense, to be honest. If you want, if 128 bits are not enough, then usually we are having such solutions. So with two I2C blocks, two I2C units connecting this same address, nodes of the same addresses to it. So for example, we have a node 1 with address 55, and then node 2 with address 55 as well, but they don't, there is no clash, no collision, because they are connected to different I2C blocks in a single microcontroller. So usually that's the way we do it. The addressing is indeed a problem from practical point of view, especially when you want to connect multiple sensors. In practice, it is done because, you know, when there is a I2C sensor, usually it has 1 to 3 address lines. So A0, A1, A2, and those address lines we connect in hardware. For example, we connect to ground and to VCC, and these address lines are generally modifying the address, I2C address of such a sensor. And that's also one of the things I find a bit funny about I2C and SPI, is that in SPI, of course, yeah, we need plenty slave select lines, and we have clock MISO and MOSI, so 3 lines. In I2C, you've got SDA and SCL. Okay, that's nice. But then we have very often, we have very often this local A0, A1, sometimes even A2 lines, which, yeah, if you sum them together, it gives us 5 lines, which is exactly even more than we have in SPI. So that's why, okay, I2C is good. I2C have some features, but sometimes, believe me, it's better to use the SPI. Okay, any more questions? Yeah, let's have then a short break. A response, a comment to this chip. Yeah, in case of I2C, there exist many strange chips. For example, extending the ports or an interface between the I2C and parallel ports, I2C and SPI. So of course there are many ideas, because the I2C is in use, and the people are using SPI for many applications. Yeah, the question is it really useful, and or would not it be possible to do it in a simpler way? And in my opinion, I2C, okay, it's not a bad interface, but it's not as good as to use it to everything and to connect everything, and then to use some special tips and tricks to complicate it even more. I'd put it this way, because the use of special chips is usually is about complicating the chips anymore. Really, what is the sense, in my opinion, to use the I2C extension chip if you can use a larger microcontroller? Today, we've got really a variety of microcontrollers on the market with not only multiple I2C blocks, but also with many pins, which means that you can use a larger case with multiple pins and use the simpler SPI, for example. But anyway, it's a discussion that we could go on forever, or for a longer time. And because we have no time, next interface a bit different from the other, from those different, but also a bit similar. One wire from the simple interface. The idea about the one wire interface is to simplify the I2C, simplify to the way where only one line is used for connection. And there are various names for this interface. I chose one wire, although there are a couple of variations depending on the manufacturer. They have different ideas about how this interface should work and how this interface should be named. Although, to be honest, the difference is small. The basic idea is common. So the idea is to have the interface that's having just one data transfer line, that line used only for transferring data. So this time we have no clocking line, which means that we return back to the idea known from UART of asynchronous data transfer. So the idea where there is no clocking transfer, the main advantage of this idea naturally is the reduction of the hardware necessary to connect between the devices, because this time we have just one data line plus naturally the ground line. So because the ground has to be delivered, the ground is common. So one signal line and one ground line, and that's enough for the connection. Yeah, so the idea is very good. Of course, not all that shines is gold, which means that this idea has some flaws. And the flaws of this idea with single wire communication is the increased complexity of the data transfer. Why the increased complexity? Because this time we have to, in case of one wire interface, this time we have to deliver. So the nodes, we have to deliver an information about the transfer speed between the nodes, and in order to make the multiple node, in order to make a data bus, also we need to deliver the addressing between the nodes. So all these two factors make this interface not that fast. I wouldn't say that it's very complex, because it isn't, but not that fast. So the standard data rates here are significantly lower than in case of I2C, and much lower as compared to the SPI. So we talk here about tens of kilobits per second, and that's it. We've got also half duplex data transfer, which means that it reduces the data transfer even more. Yet the good thing about it is that, really the good thing, and this is the major advantage, is that we have a serial one-wire interface. Also something which is very useful sometimes is that the communication can be used. This communication wire also can be used for delivering power supplies. Sometimes, how does it work with the power supply? Here we are, the schematic, electrical one. And in the master of data transfer, because this one of the device has to be a master, yet any can be a master in practice. Theoretically, anybody can be a master, because there is just one line. Anybody can draft the line. In practice, we have one device that is microcontroller, and the other are usually sensors, which means that microcontroller is a master, natural master, becomes a natural master, while the sensors are becoming natural slaves. And in the master, we've got the puller. And if there is nothing happening on the line, then we have a high voltage, which then through this diode charges those capacitors. So same as here, we have the current flowing, charging this capacitor. And if the sensor is not requiring a lot of power, a lot of electricity, then the charge on this capacitor will be enough to supply them. So that's the way the power supply is delivered to the slaves in case of one wire or single wire interfaces. Yet this is noisy. So the bad thing about this supply is that it's noisy, and to be honest, if you would like to supply a good quality sensor, never use this kind of power supply. If this is to measure with temperature, let's say with 1 degree precision, it's okay. But if you want to get to 0.1 degree, never use this method. We have, in case of the data transfer, in case of one wire, begins with a sequence that is called a presence detection. So it's something like a start bit in case of I2C, but this time we don't have two lines, we have just single line. So the start bit looks slightly different. How does it look? Normally the line is kept high, and if a master wants to start the data transfer, it then keeps the line low for circa about 500 microseconds. Then it releases the line and samples the line after between 15 and 60 microseconds. If there are any slaves on the line, then any of those slaves, because all the slaves should then pull the line low. We have a pull up, and we have, of course, open drain configuration, same like in I2C. So we can do it. So any slave can drive the line low. Then it means the master knows then there is a slave on the line connected to the line, because there is no addressing in this phase. It's just about checking if there is anything connected to the line, anything worth talking to. So this is on the physical level, checking presence on the physical level. So it's a bit different, mind that, from the I2C, because in I2C there was acknowledge, but the acknowledge was after sending an address, which means that the acknowledge in I2C is set by a dedicated slave. Here every slave connected to the line has to pull the line low during the presence detection. That's how the presence detection is working. And then reading and writing, again, a bit strange, because we have, again, no thing like direction in one wire. Here the writing and reading line is done on the bit level, not on the byte level, but on the bit level. So writing one means that the master pulls the line low for a moment and then releases the line. Then a slave device samples the line and sees the line high. Take a look about the timing. So the timing is critical here. It is very, very bad, the timing here. It's very, very bad that we have the timing, and that it's so dedicated to timing, because it means that we have to stick to those times, which means that they are not very small times, but also not very long ones, which means that we have to be, if we would like to do to implement the one wire block by ourselves, then we have to really spend a lot of time just during the data transfer, wasting a lot of time during the data transfer. And this is something we really hate during the development of embedded system applications. So generally, this is a very, very nasty feature. That's why crying face here. Reading is done in a similar way. So also master pulls the line low, so triggers the reading, but then the master waits this 15 microsecond time, and after this time it samples the line reading. If we have line, if we have low or high state, then reads 0 or 1 is read here. Generally, the method, which is very nasty, of course, it is required because of it is needed because of the requirements of the wish to have a single line communication, but still very, very nasty method. That should be used only in special cases, not on everyday basis. In case of micro one wire, we have also MAC layer, so medium access control layer, with the addressing. So the data, so we have a certain frame with this present sequence or reset sequence, whatever we call it, in the beginning, but then begins the addressing. So we still have the addressing. We have the addressing being sent, and then this addressing is not really acknowledged, unlike in I2C. But then we've got the functions being delivered, and depending on the functions, it's either reading or writing, and any number of bits or bytes is then transferred. We don't have any stop bits or start bits, so nothing like this here, just a reset sequence to renew the communication by the master and one master on the line, dedicated, although not physically, but dedicated, because honestly, connecting with this interface to microcontrollers have very, very tiny sense. That's why we communicate a microcontroller and something simpler like a memory. So here I have an example of a one-wire device with 64-bit addressing, because the one-wire is yeah, you know, it was used, I remember it's it was about 15, maybe 20 years ago. There was an access system done on one-wire chips, on one-wire memories with this 64-bit IDs. Then during one-wire interface, those IDs were read by, so each student had such a dedicated one-wire chip that allowed him or her to enter the dormitories on VPGA, for example. Now it's wireless, but it used to be in the beginnings, in the first phase, it was realized during with the 64-bit ROM ID. Nobody is using this system anymore. So today everybody likes wireless. So NFC took over this functionality. Yet it used to be something like this in the past. Any questions about the one wire? Can't hear any. What's the sense of using one wire today? Maybe that should be the question. Honestly, the one wire today, the only use I can see is the use in sensors. If you have a sensors and you don't want them to be wireless, because you're afraid of the battery. So you don't want to change the battery every time, so every couple of months or a couple of years maybe. Then we connect the one wire tape sensor to a microcontroller. And then one wire, because then one wire has a sense because we have fewer cables, which means that we can connect this, especially if you use a parasite power. If you don't need high precision, then we can connect a one wire sensor over 5 or more or longer wire, and then yeah, spare some cash or reduce the cost of the whole system. Yet honestly, the sense of it is very tiny today. So first of all, we've got the wireless interfaces like Bluetooth, like Zigbee, like OpenThread, and also we've got the access systems based on the NFC. So today, the sense of one wire is very little, which we can't say about this about the next interface that I want to talk about. This is CAN. But before I talk about it, I have to grab a power supply to my computer. So give me 2 minutes. And I'm back with a power supply because my computer seems to be dying. Moments. Excuse me for a moment. I'm back almost. There. Okay, we can continue. Sorry for the interruption. CAN. What is CAN? What's the idea of the CAN? CAN, from its beginning, was designed to work in harsh environments. So in the environment where the amount of various noises, electromagnetic noises, is high. That's why it was from the start designed to deliver high quality communication, maybe not the fastest one, but high quality and reliable communication between multiple nodes, because of another advantage of the CAN interface. So another important feature is that it delivers, it allows for networking here. In case of CAN interface, moreover, we don't have it only in the physical layer. So it's not only physical layer which is defined, not only MAC layer which is defined, but also partly we can call that we have a link layer defined. So a part at least of a link layer is present here, which means that we have kind of routing here in case of, well, let's say it's in case of CAN interfaces, yeah, it's maybe a bit preemptive, but still we can say that it's a part even of the layer 3 in our four layer model. So CAN interface in general, in order to work in harsh environments, it has a couple of features for this operation, for this kind of multi-master multiple nodes environment. First of all, it's physically constructed to work on two-wire differential interface. So we have no more single wire, we have two wire, although the two wire is single signal, because we have two wires, but we have, like in one wire mentioned just a moment ago, we have a single lane where the transmission is going on, yet transmitted over two wires, and this changes a lot. So the data rate from mere 15 kilobits per second, here we've got 1 megabit per second. So that's the advantage. Because we have one wire, we have of course half duplex data transfer, but we've got point-to-point transmission, of course, but we've got a multi-master architecture. That's a very strong part, another strong part of the CAN interface, multi-master architecture. So anybody that transfers, starts to transfer, controls the line, and anybody can transfer, or any node can transfer to any node here. So that's the way. That's the way it is. Because of the differential interface, they are very nice distances. The differential interface and not the highest data rate, because in case of basic CAN, because we've got a couple of versions of CAN, to be honest, but we will talk just about the very basic one, so 20A and 20B. In this very basic CAN, we've got up to 40 meters of data of the link length. That's of course because of differential data transfer and relatively small data rate. So 1 megabit per second is today nothing really very special, but here it is. And yet the differential data transfer and small data rate is not everything that we have. It's not everything that we have in order to give us the high reliability of the data transmission. So the next thing important is this one. So bus access with bit arbitration, because we have, in case of CAN interface, also the mechanism of multiple access, like in I2C. So also we have a carrier sense multiple access. So this is the same. Yet in case of CAN interface, instead of detection of collision, we've got something more. So we've got collision avoidance, and avoidance of the collision is done through this so-called bit arbitration. So this bit arbitration in CAN gives us avoiding of collision. So if there are two frames being transmitted at the same time, the nodes are controlling what is present on the line. So this is this detection of transmission errors by each node. And the nodes which are transmitting the data are controlling the line itself. And if there is any mismatch between the data which should be on the line and which are on the line, then the node transmitting those data or detecting this problem simply shuts down the data transfer. So this is what is meant by collision avoidance. So this is different from collision detection known in Ethernet and in I2C, because in I2C, in I2C the collision detection is not automatic. Although we can say that it's there, in Ethernet it's more automatic, yet the collision detection in those two interfaces means that the data transferred are lost. In case of collision avoidance in CAN interface, the data with the highest priority or privileged addresses, they pass through, so they are still delivered from the source to the destination node. So that's a bit difference, making everything more complex at one side, but having a bit high reliability of data transfer on the other side. Also, take a look, we have a very nice feature, especially compared to I2C. There was a question about this mere 128 possible addresses in case of 127 addresses in case of I2C. Here in CAN interface, we've got either 2038 addresses with 11-bit identifying CAN to 0A. In CAN to 0B, we've got even 29-bit identifier with 536 million variations, millions of addresses available on the bus, which means that the CAN interface is much more into multiple nodes, not really physical, because I can't imagine connecting 2000 physical nodes to the line without dedicated buffers. It's really not possible. Too high capacitances of the line would be, and too many physical problems, electrical problems. Yet it's not a problem to connect 2000 logical nodes to the line, because in case of CAN interface, there can be multiple logical nodes in one physical one and in one physical node, and that's that's why we have such a large or huge addressing space compared to the interface like I2C, for example. 564 and 36 million possibilities. CAN interface is, of course, today very popular in cars. So this is the basic communication interface. It's not very fast, so it's not the only interface used in cars, because there is a UART relative CAN lean interface used as well. There are various multimedia interfaces. There are also a CAN alterations available, especially for multimedia. Exactly, multimedia data transfer, for multimedia networking inside the car. So there are various ideas today, but the CAN is still playing a crucial role in connecting, especially the basic instruments and basic sensors and the basic control of the main control, maybe not even the basic, but the main control of our cars today. So we've got various, for example, lights, ABS systems, windows, steering, instrument panel, transmission, engine compartment. Everything is today relying on this CAN communication, on this CAN interface. Yet it doesn't mean that we can't use it in our application. But in case of CAN interface, it's interesting because we've got beside this physical, which layers that I mentioned, MAC, and partly a network layer, because it's like mentioned, link layer, network. Sorry, of course, this is link layer, LNK. Nobody corrected me. Network layer, partly the network layer. Sometimes in CAN, we can find also an application layer. So we don't need to use it because it's not inside a microcontroller, but we can use it. And the application layer, the application layers, some of them are free, implemented like CAN Open. Some of them are not really free, like the examples you have here on the slide. They simplify a lot communication between various modules. For example, we don't need with the proper application layer, we don't need to play with the addressing, with the arbitration. When communicating, for example, with a windshield or with an engine, just then we use the appropriate application layer, and we are just communicating with an engine. We don't care about what's underneath. We just send a command, ignite, and that's it, and the engine starts. Engine start, like in one nice film. That's what we do with the application layer. The problem with the application layers is that mostly they have to be paid extra, and because they are dedicated to certain cars or certain application areas. If you want to use the application layer in your design, in your device, then the CAN open, I think, is the solution that should be considered. Or you can use just the very bare CAN interface, with just placing the data, in taking care about the data fragmentation and defragmentation by yourself, because the application layer is mainly for this. Physically, the CAN, CAN can be the physical layer. Honestly, there are various physical layers available on the market, because CAN is used so widely, so that not only differential line is used here, is available here, but also there is a fiber version, there is a single line version. Yet the differential is the most common. So we have usually CAN L and CAN H. So CAN high, CAN low, terminated at both sides to avoid reflections on the line. We can have a grounding, which is not really that critical. CAN devices, because we have differential lines, CAN devices are synchronizing thanks to the so-called NRZ coding and with the bit stuffing. What's this? In a moment. So NRZ coding and bit stuffing. Here we have the idea how the frame looks like, CAN frame, without the bit stuffing itself. So the very basic CAN frame. And here, take a look about two. So there are a couple of interesting things here on this slide. First thing, the data transfer is not byte wide anymore. So we have there is a control field with the data length field, but the data length, and the data length tells us about the field, how many data bytes there will be. So okay, we have data bytes here, but the data frame length is completely is independent on the byte, and it's no longer just 1 byte or 2 bytes. Here we have the data entangled into a frame with arbitration field here, this 11-bit arbitration field, but there is also a 29-bit tape frame with some basic controls, and with the CRC frame. And here is something else that I want you to point out. A next mechanism beside beside the differential line and beside the CA, so collision avoidance, that's giving us the strength of data transfer or reliability of data transfer of this interface. So these are two more mechanisms. Mechanism number 3, in fact, this is the CRC. CRC, so cyclic redundancy check. So it's dividing the remainder of the division by a polynomial. So that's what CRC is. But here the CRC is very long compared to the length of the frame. Mark that the control field can be 0, which means that the data field may be absent from the frame. So it is possible to send in CAN empty frame just to send the frame, because there is the arbitration field. Here is the arbitrational address field, because they are the two names. The functionality, the name of the field is arbitration, but it has two functionalities of being arbitration and the destination address of the node. So it's like in CAN, like in I2C check block, because we've got the destination address. But we've got the CRC field, which is 16-bit, that may cover only 16 bits of data, which means that the CRC is very strong. So it means that the protection is very good. So that's why this is mechanism number 3. Yet it's not the last mechanism for having the CAN interface being so reliable. Here is mechanism number 4. What's this? It's the acknowledgement. Acknowledgement, which is known in I2C for acknowledging of 1 byte of data. Here, the acknowledgement is a bit weaker because we don't acknowledge the whole, we don't acknowledge every byte, but the whole frame is still acknowledged, which means that if a device that transmits the data, if the master of the transfer sent a frame to a destination that is known, and the destination node received frame in a proper way, so with the proper CRC, proper arbitration field value, and proper CRC field value, then it issues it sets the acknowledgement. Otherwise, it's not, the frame is not acknowledged, which is a simple information for the master that the information should be resent. Very simple, very powerful, not generating unnecessary data transfer on the field. So this is really feature number 3 and 4, very strong features in this protocol. And the last thing today, because we're almost at break, the bit stuffing. If you notice anything like this, if you find it in the literature, there is a feature of this protocol for synchronizing the data, because we don't have a clock line. But in order to keep in order to alleviate or to simplify the bit. The speed mismatch, clock mismatch between transmitter and receiver, here there is an additional synchronization happening. The synchronization needs switching. So the more switching, the better for the PLLs inside the receiver, or for the circuitry inside the receiver. And in telecommunication, in various interfaces, not only in CAN, but in various more or less complex interfaces that are working with this mechanism of self-synchronization of data stream, there is used a special bit stuffing feature, which you can see here as violet ones. The bit stuffing means that it's a simple mechanism, theoretically simple, where after each 5 zeros there is artificial 1 inserted. So 5 zeros, 1 inserted, 5 zeros, 1 inserted. So it's bit stuffing. Take a look, more switching on the bottom chart than on the top one. Then during the reception, this switching is used only for synchronization, for generating a local clock or for adapting the clock rate. And then after this functionality, the signal is bit stuffed. So it is moved back to this form, and then it is analyzed. So then CRC is checked, arbitration field is checked first, and CRC is checked, and only then the data are received. But then it's not all. But more about it. Yeah, the data stream. To finish, it's not all. So that we have also some interesting mechanisms on the higher level, like the messages and like the mailboxes, but more about this already next week. And to finish, 2 more things. First, the data stream is pulled. So the question is fed into PLL for tuning. Yes, it can be. It depends on the CAN reception, because the CAN receiver it's not really synchronizing. So it doesn't have to be a PLL there. So PLL is necessary for Ethernet. In case of CAN, it may be used, but it doesn't have to be. Usually the CAN is not as complex as to include a PLL. Yet sometimes there really exists a PLL inside. Also, but even if it does not exist a PLL, then this synchronization bits are used to synchronize additionally the bit rates, because you know, the transmitter and receiver here has to know the bit rate, the baud rate. So it's like in UART, but because of the clock differences, there may be an error and there may be a mismatch. And in order to avoid this mismatch, this switching is used during the synchronization. So of course it can be used at PLL, but there are also other techniques, a bit simpler ones, not as universal, with digital circuitry for synchronizing the clock. So sometimes the so-called DLLs are used, not PLLs. That's how it is. Any more questions? If no, thank you again for your attention. If you want some consultations, I'm available tomorrow at the university. Next week, a lecture as well in the same way. So if you want to come to 105, you're welcomed. If not, just I hope to see you on Zoom. Thank you very much for today and have a nice afternoon. Goodbye.
All right. Goodbye.
Goodbye.